The topic for today is it's actually a very interesting topic, which sort of connects lots of the things that we've been discussing over the past lectures, and that is integrality of polyhedra. It's a very important topic in combinatorial optimization, and you'll see that there is a beautiful theory that underlies many of the results that we've obtained so far. So let me first start with, start by writing a few linear programs and some of the surprising things about them. So let me start with the min-weight bipartite matching. So this is the most recent one we've seen. And so it was something of the form, and I'm writing the LP below it. X delta V is equal to 1 for all V, and X was greater than 0. Recall that delta V is just equal to all the edges, where the edges contain V. Right, so here was min-weight bipartite matching. Let me also recall the min-cut linear program. So that was of the form, now you might not remember it, but let me just write it down. And then it was for all edges UV, we had these variables Z that would form distance labels, plus and the y's, which are also variables. So zs is equal to 0, zt is equal to 1, and y's were greater than 0. So y's were also labels, variables that you put, and then you had these distance labels. So this is min cut. And then let's look at min cost flow. So let's look at min cost flow. So then there was another minimizing of, there was some sort of price that we had, and we had these flow conservation constraints. So for all V, we had X of delta plus V minus X of delta minus V, because in this case we think of the graph as directed. Delta plus V are the edges leaving V, and delta minus V are the edges going into V. This was equal to BV. This was the demand. And then we had, for all E, XE was at most some capacity, and X was greater than 0. And in the transshipment problem, we did not have that last, capacity constraints. So, and just to remind you that X of some subset, so for F is a subset of the edges, then XF was simply the sum of XE, where E was an edge. Okay, so we had these three linear programs, and the surprise, and some of you actually noted this, we explicitly called this out for bipartite matching, that the solutions came out to be integral. And this we proved explicitly using Birkhoff's theorem. For the min-cut, we proved it using the rounding scheme of Garg, Vazirani, Yanakakis. It was a fairly non-trivial theorem. And for min-cost flow, okay, so let me say that, for min-cost flow, actually the proof that the solution has integer coordinates is actually by Ford-Fulkerson. Or if you think about the augmenting cycle algorithm, then you will see that you will get an integral flow. So we assume all constants are integers. Right? That's sort of the default assumption that we have. So assuming that all constants are integers, the solutions, which is essentially two things, which is the optimal value, and also the optimal point, are integral. So technically the optimal point is just saying that there exists an integer optimal. That's what I mean by integral, because there may be a non-integral optimum, but there always exists an integer optimum, and the optimal value is always an integer. This is by no means non-trivial. There's no reason why this linear program should actually give you an integral point for min cut, or for min cost flow. Although we did not discuss this while talking flow explicitly, the solutions that we got were actually integral flows. So this is, you know, one can think of it as some kind of a surprise. Of a surprise, because a linear program has a discrete or an integral solution. And if you think about it, there's no reason why this should be the case. So I'm just going to draw a very simple example, and you know, you can come up with various examples as well. There's no reason why a polytope, so the polytopes defined, so let me, you know, here's the objective, but here are the polytopes. There's no reason why the polytope should have integer points. So just to give you a simple example, suppose you took x plus 2y is less than or equal to 3, and x and y are greater than or equal to 0. You can plot something like this, and it's easy to see that when x is equal to 0, then the y is going to be 3/2. So you have that 3/2, and that's your polytope right there. And so the coordinates of that point are not an integer. So there's no reason why integral constraints should lead to integer points. And these polytopes, the polytopes, are called integral. And what we'll study today is an underlying theory that actually explains all of these. Why do all of these polytopes end up having integer points? Before we get into the...
So when you say all these polytopes, you mean these specific three,
these three,
right? Not general LPs.
Not general LPs. There's no reason why a general LP should be integral. For example, I've shown an LP here which is not integral. Very simple LP.
Right, yeah.
And you can come up with like more versions of these. It's obvious. You should think of it that this is an absolute mystery, or it's magical that the solution should be integral. And I just want to write out, just so that you see this, you know, how did we prove that they're integral? So for the bipartite matching case, this was Birkhoff's theorem. For min cut, we proved it through randomized rounding. It's a fairly roundabout proof actually. And then for min cost flow, we never explicitly proved this, but technically it follows by Ford-Fulkerson. It follows by the augmenting path algorithm. It follows by the augmenting path, or augmenting, you know, I would say cycle or the augmenting path. Because you can look at the min cost flow as a generalization of max flow. So the augmenting cycle or augmenting path algorithm proves this is integral. This has a name. This is also referred to as the integrality of flow. Okay. So any questions at this point? So this is the topic for today. We're going to see an underlying theory that explains all of these phenomena. Okay. I'm going to take a slight digression now, and I just want to talk about these problems at sort of a more abstract level, to talk about convex hulls of integral points. And then we'll come back and then I'll give you the answer for this. So in the cases that we saw above, instead of thinking of the LP, think of the actual optimization problem that we wanted to solve. So think of the optimization problem that we wanted to solve. So what we do is we want to optimize over an exponential number of discrete objects. And so I'll say linear. We're talking about linear optimizations. And what were these? These were matchings. There were cuts, and there were integral flows. So sometimes you can state the flow problem as you want an integral flow. You want a flow where all the flows are actually integers. And so this gives you some discrete set. And so for each specific object, so for example, think of a matching. Let X be the incidence vector, or some integral vector representing the object, and you want to perform an optimization over all of these. So for example, the incidence vector here would have just been xe is equal to 1 if and only if E is in the matching and it's 0 otherwise. Or you could think of it, if it's a flow, then you have the flow values. So let X be the set of points. And we're trying to optimize some link. So what we're trying to solve is we want to maybe min or max X and X C transpose X, min or max. And this, at the face of it, seems like this is, in general, would be NP hard. So how do we deal with this problem? We say, okay, suppose we could do the following. Let's instead say, let's minimize X chosen in the convex hull of capital X, C transpose X. So let me just define the convex hull. And this is the convex hull of X is the set of all convex combinations of X, specifically, so I'll just say that CH of X is equal to all the points of the form summation lambda X times X, where X is in your capital set, where the lambda X is always in 0 and 1, and the summation of lambda X is equal to 1. Right? This is a convex combination. So think of it like a distribution. So the convex hull is like, the distributions of all points, set of all convex combinations. And what you can argue is that, CHX is a polytope with vertices exactly a subset of capital X. This is just looking at the geometry. So, just to draw a little picture, the convex hull of, let's say, these points in 3 dimensions is like, this 3-dimensional object. So it gives you a polytope. So a polytope can be defined both by the faces, but you can also define it by the vertices and say it's a convex hull of these. Now the nice thing about this is this problem can be solved by an LP. And indeed, this is just equal. So you can optimize this discrete optimization problem can be converted to an LP, but now you have a problem. How do you represent the convex hull of X? How to represent the convex hull of X through a polynomial number of constraints. And in general, I won't get into this, but we can also say that instead, or even if you don't have a polynomial number of constraints, if you have a separation oracle, then you can use ellipsoid. But let's not get into that. And what we actually have for these cases is an alternate way of thinking about each of these, is that these actually give you representations of the convex hull of matchings, the convex hull of cuts, and the convex hull of integral flows. Not all integral flows, but some specific subset of integral flows. So essentially, all the flows that satisfy the capacity constraint and the demand constraint, this is the convex hull of all integral solutions for this problem. This is the convex hull of all incidence vectors of ST cuts. This is the convex hull of all perfect matchings. So that is the connection to convex hulls. I'm not going to get too much into convex geometry here, but this sort of hopefully gives you some more context as to another way of looking at this from the perspective of convex hulls. Any questions? Okay. So with that, let me now get back to our main point here to try to understand why these polytopes ended up being integral. Why these polytopes are integral. So first I'm going to define what an integral polytope is, and then I'll tell you sort of the basic, the theory. So a polytope P is integral. It's sort of the obvious thing if all vertices of P have integer coordinates. Right? This is sort of the obvious definition to have. I'm going to give some equivalences for this definition. So this is not, so technically this is, I should call this this is a lemma, which gives equivalences, and which will say just alternate ways in which you can write this condition. A polytope P is integral if it is the convex hull of integral points. And this I should say if and only if, because this is a lemma, this is not a definition. And another convenience one is that polytope P is integral if and only if for all integral objectives C, the min or the max, the min of C transpose X for C in the polytope, if this min is an integer. So these are all essentially equivalent. The most natural thing to define an integral polytope is just to say that all the vertices have integer coordinates. As we argued that a polytope is integral, so because this is a polytope, this is bounded. So a polytope is integral if and only if it is the convex hull of integer points. And again, I'm assuming that things are bounded here. Things are like, it's not an unbounded polyhedron. And a polytope is integral if and only if for all integral objectives, the optimum value, not the point, the optimum value is integers. The nice thing about definition, or the lemma part 2, is that it basically says that you don't have to think about the actual point as long as you can argue that the objective value is an integer. But interestingly, you can prove that it's equivalent to showing that all the vertices have integer coordinates. Any questions about what I've said so far? Any questions? Right? All right, so now let us talk about our main characterization. And this is called totally unimodular, also called TU matrices. Another way of framing what we've discussed so far is asking, when is ax plus b, ax less than or equal to b, integral, right? Because this gives a polytope. So when is this polytope integral? And remarkably, there is a fairly clean answer to this. So I'm going to define a matrix A is totally unimodular if for all square submatrices A prime of A, the determinant of A prime is either -1, 0, or 1. A matrix is totally unimodular if for all square submatrices. So take any matrix, and what you do is you take any square submatrix, and the determinant is either -1, 0, or 1. All right. So note that all entries of A, of a totally unimodular A, are in -1, 0, or 1. Obviously, because each entry is a square submatrix of just 1 cross 1 submatrix. And so a theorem, an important theorem in polyhedral combinatorics of Hoffmann and Kruskal, and this is from 56, says let A be let A be a totally unimodular matrix. Then let me state something else. Let A be a totally unimodular matrix and B be an integral vector. Then Ax less than or equal to B is integral. So hopefully this makes sense. By Ax equal to B, technically I mean the polytope. I mean the polytope given by Ax less than or equal to B. So if you take a totally unimodular matrix and you solve Ax less than or equal to B, so you consider the polytope given by Ax less than or equal to B, then it is integral. And remarkably, there's actually another theorem, again by Hoffmann and Kruskal, which is even stronger. What it says is Ax less than B, x greater than 0. So this polytope, where you have non-negativity constraints, is integral for all integral B if and only if A is totally unimodular. So total unimodularity seems to really capture the notion of Ax less than or equal to B being integral. This is for all B though. You do have matrices which are integral for a specific choice of B, but are not totally unimodular. What this says is that if A is totally unimodular, then regardless of what B is, the matrix, the polytope is integral. And indeed, what happens in all the cases that we have seen so far is that the matrices are totally unimodular. And so that gives this underlying explanation of why we've got integral solutions for all these LPs. So the Hoffman-Kruskal theorem essentially explains why that is the case. Any questions about what the Hoffman-Kruskal theorem is?
Not a question, but how is the second statement, like how does it go? It seems very unnatural for this to be true for any D.
So I'm going to prove this theorem. So you'll see the proof, yeah. But maybe one way of looking at this is, let me show you just min-cost flow. And note that min-cost flow, the flow happens to be integral regardless of what the demands and the capacities are, as long as those are integer. It turns out that there are variants of this even for min-cut and for min-weight bipartite matching. So the constants over here are this 1, right? It basically says you want a matching. But if you actually replace the 1 with a 2, or you even gave different constants to each vertex, then you can argue again then that if there is a solution, then you'll have an integral solution. So it is remarkable that there should even it is, at the face of it, it seems kind of unimaginable that there would even be a matrix that said this would be true, that regardless of what B is, you end up with an integer solution, as long as B is integral, of course. But that's sort of the magic of total unimodularity.
Yeah, I was thinking about just a simple two-dimensional case, but I think I answered my own question because I forgot the condition for the matrix having entries between 1, 0 and -1, which would imply that it's on R2 it's essentially 4 orientations of lengths.
Exactly. So actually what that shows you is one side. What is remarkable is the other side as well. That integrality for all B. It's an if and only if. So the first version is only an implication in one direction. It just talks about AX less than B. But I think Hoffman and Kruskal proved both theorems. And I think maybe the latter one is the one that's actually called the Hoffman-Kruskal theorem. Like this one is the HK theorem. And it completely characterizes, it says that A is totally unimodular if and only if AX less than equal to B with X greater than equal to 0, if that with the non-negativity constraints is integral for all B. And as I said, all the matrices that we've seen so far, like the ones that I showed you, and the problems that we have solved happen to be totally unimodular matrices. So the plan for today is to prove the second Hoffman-Kruskal theorem. So actually the first one is a consequence of the second one. So I'm going to leave that as an exercise and I'll put out notes on that. But the second theorem is the one that I'm going to prove. Because of this if and only if, it's quite remarkable that you can even characterize. The proof is surprisingly simple and elementary. Just a little bit of linear algebra and not much more than that. And then we'll get through that, and then what I would like to show you is why those polytopes we got were totally unimodular. Even proving that a specific matrix is totally unimodular is sort of non-trivial, right? I mean, how does one argue about all square submatrices? So it turns out there are even more convenient characterizations which you can apply to see those. But not convenient characterizations. There are certain sufficient conditions that you can use. Okay.
Another question. Mm-hmm. So the second theorem is actually pretty strong because it says this is true for all B.
Yes.
How about if we restrict B to some nice variables, then can we broaden the class of A?
That's a good question. That in some sense, you're getting into like the field of polyhedral combinatorics. I am not aware of any nice restriction on B that allows for something like this. On the other hand, even though this seems like such a strict condition, many matrices that appear in optimization happen to be totally unimodular, sort of demonstrating the utility, even though this condition seems so general, actually, and I will show you, there's a paper from AAAI in 2020, right, like last year, talking about fairness in clustering, and the main result is to show that if you write out an LP for this, then it's totally unimodular. Right, so it's a very very useful thing to know, this notion of total unimodularity. Okay, so let's...
Can I interrupt you?
Yeah, sure, go on. Yeah.
So, do we know in what kind of LPs the matrix is not totally unimodular? Does it appear at all in any broad class of problems?
Class of problems, I mean, definitely they appear a lot, right? So because you could imagine entries that are not in -1, 0, 1, 0, and 1.
Maybe they can be reduced to equivalent LPs, right?
So this is now, the big question whether you can do it. But you know that typically when problems are NP hard, when you take an LP relaxation, you are not going to get total unimodularity because you know that the points are not going to be integral. So for example, if you write an LP for vertex cover, which we'll actually do in the next lecture, or you write an LP for set cover.
Yeah, that's not totally unimodular.
It cannot...
Because
yeah.
Integer program is strictly harder than the linear program.
Exactly. So there happen to be enough cases. So you're asking what kinds of... Are there polytopes that come up which are not totally unimodular, yet you get some kind of integrality condition?
Mm-hmm.
The answer is yes. I mean, there are more complex methods. So actually, another way of looking at this problem is, let's say you're trying to actually compute what CH of X is, the convex hull of some discrete set. Then you can try to come up with polytopes through some mechanism called a cutting plane proof, which will give you like an explicit description, but it might be very large. And there you may not necessarily get totally unimodular matrices. Indeed, for example, just for general matchings, not for bipartite matching. So general matchings, there is something called the Edmonds Polytope, which is actually an exponentially large polytope, but it turns out that it can be solved in polynomial time. And I don't actually, I'm not sure whether that, I don't think that is totally unimodular, but I should check.
But does total unimodularity have anything to do with flows specifically?
So ask me this question at the end, and I'll have a better answer given the concepts I'll teach.
Yeah.
Okay, so let's prove the Hoffman-Kruskal theorem, and just let me recall to you this fact that you may have learned in high school, which is Kramer's rule. So Kramer's rule says, consider AX equal to B, A is square, non-singular. Then, there's the solution is given by xi equal to the determinant of ai divided by the determinant of a, where ai is a with the ith column replaced by b. Right, so it just says that here's your square submatrix. You want to solve ax equal to b. This is x, here's a and b. And ai is, you could take the ith column, replace it with b. You compute the determinant, and this gives you the solution. Okay. Now it turns out that this basic theorem that we all know from high school is actually just going to be the key tool that we use to prove the Hoffman-Kruskal theorem. So I'll start with the proposition. So I'll say A is square, so it's a square matrix, integral. So I'll say integer entries, and full rank, so it's non-singular. Then Ax equal to b, or the solution of Ax equal to b is integral for all b if and only if the determinant of A has an absolute value of 1. Right? So you have a square matrix that is integral and it has full rank. So it's going to satisfy the conditions of Kramer's rule. The solution Ax equal to b is integral for all b if and only if the determinant is either 1 or minus 1. Okay? So this is, again, you start seeing this sort of something being integral for all b. And it ends up implying something very natural about the determinant. Okay, so we can prove this. It turns out to, it's a relatively simple proposition to prove. Show you the proposition once more. So, the reverse implication is quite easy. So if the absolute value of the determinant is 1, then by Kramer's rule, xi, the absolute value of xi is just equal to the absolute value of the determinant of ai, which is going to be an integer, right? Because all the entries that we're talking about are integral. So if the determinant is 1, then by Kramer's rule, all of these are integers, and we're done. Okay, now let's look at the reverse implication. So note that the matrix A inverse is the solution of the matrix equation Ax is equal to the identity matrix. Now by the hypothesis, what is our hypothesis? Now we're saying that suppose Ax equal to b is integral for all integral b. Is all, I should say all integral b. So by the hypothesis, Ax equal to ei, where this is the unit vector, is integral, or I should say the solution of Ax equal to ei is integral. Ei is the unit vector, is the ith unit vector. Hence, essentially, if you solve this, the solution of Ax equal to I is integral. So A inverse has integer entries. The determinant of A times the determinant of A inverse is equal to 1, but both are integers. But the determinant of A and the determinant of A inverse are integers, right? That's by assumption. That's what we just showed, that A inverse has integer entries. Hence, the determinant of A is plus minus 1. It's plus 1 or minus 1, and that ends our proof. Okay, this is a fairly simple proposition. So if A is square, it has integral entries and it has full rank. And the reason we needed all of these conditions here is so that we can apply Kramer's rule. Then Ax equal to b is integral for all integral b, or the solution of Ax equal to b is integral for all integral b, if and only if the determinant of A has an absolute value of 1. Okay, and you see this, we got a 1 over here. Absolute value being 1 is very related to total unimodularity, so we just have to build on this and we will get our proof. Okay, so the proof that I'm actually going to describe is by is not by Hoffmann-Kruskal, it's by Venard and Danzig, and it's a much simpler proof. So as an intermediate definition, we'll say a matrix in M cross N, matrix A of full row rank is called rank unimodular, or we'll just say unimodular, if each basis of columns has determinant plus minus 1. So what do I mean here? So we have some matrix of full row rank. So we have M, here's N, and because it's a full row rank, M is less than or equal to N. So we can look at any subset of columns. So consider M columns. I'm going to call this submatrix B. I'm going to call these columns B. So if I have this matrix A, I can look at the matrix A sub B with just those B columns. And what we're saying is if B is a basis, then the determinant has absolute value 1. Of course, if it is not a basis, then the determinant is 0. So another way of saying this is really that for all square for any subset of M columns, the determinant is either 0, 1, or minus 1. That's the same thing as rank unimodular, although I will just keep this definition. And so a theorem, and this is by Venard and Danzig, and this is 68, so this is actually a proof. This is an approach to total unimodularity which came after Hoffmann and Kruskal that gave a simpler proof. So they said consider this other polytope, and if you look at this polytope, this is exactly what is considered by the simplex algorithm. Ax equal to b, x greater than or equal to 0. So consider the polytope ax equal to 0, ax equal to b, x greater than or equal to 0 is integral for all integral b if and only if A is unimodular. So here we're looking at this polytope Ax is equal to B with a non-negativity constraint, and this is exactly what you get by, if you recall, for the simplex algorithm, by putting slack variables, this is what we got. And so this polytope is integral for all integral B if and only if A is unimodular, which means that if you take any basis, then the determinant, the determinant is plus minus 1. So let me first prove the reverse implication, show that if A is unimodular, then prove that this matrix is actually integral. Okay, so now I'm going to draw some pictures here just so that you recall, and then we will need some theorems that we proved during the simplex algorithm. So let's look at Ax is equal to B. So A, here's x. So Ax is equal to B, and x is greater than or equal to 0. Now, I'm just going to recall from our discussion of solving LPs, we had defined this notion of a slack form, which was Ax equal to Bx greater than or equal to 0, which is exactly what we had. We had the rows being linearly independent, which is again, now we have a matrix of full row rank. And so this is the situation we had. And if you see, like a lot of the pictures that we drew over here, we had this notion of a basic feasible solution. So the restriction of A to some subset of columns which formed a basis. And we had this notion of a basic feasible solution, which again we're going to use over here. Recall that we had a notion, we proved, or actually we stated this as a claim, I don't think we explicitly, we didn't prove it. A feasible point is a vertex of the polytope. And this condition of a vertex is important for us because this is how we will talk about like integer vertices being integral. If and only if there exists no direction such that if you perturb in that direction, it's still in the polytope. Another way of saying this is that if there existed a direction, that is W, where by perturbing the point V along W, it stayed in the polytope, along both the positive and the negative direction, then the point cannot be a vertex. Right? So a feasible point is a vertex of the polytope if these conditions are satisfied. What we then proved, and this is the claim that we are going to use right now, is that any vertex of the LP or the polyhedron has at most m non-zero coordinates. Any vertex has at most m non-zero coordinates, where m was essentially the row rank, or in this case, the row rank is the number of rows, so it is m. So any vertex has at most m non-zero coordinates. And we are going to use this in proving the theorem of Venard and Danzig. So we'll say we have this situation Ax is equal to b. We want to argue that if A is unimodular, then for all integral b, the vertices are going to be integral. And we know that a vertex has at most m non-zero coordinates. Okay, so I will just, I'm just going to write this down over here. Keep this. Keep this over here. All right. Okay. So what we have is from the previous claim, which I showed you, any vertex of the polytope P. So in this case, this is the polytope P, or this is the polytope P over here. So any vertex of the polytope has at most m non-zero coordinates. Okay, so fix a vertex, and let n be the subset of non-zero coordinates. So here maybe a bunch of things over here, right? And these will translate to some columns here. So we can look at the columns of A corresponding to n. Now I'll just state a fact over here, and then you can ask me questions about this later on. That n, or an, must have linearly independent columns. So I'll just fix a vertex that I will refer to as V, since V is a vertex. So if you actually look at that proof, if you look at any vertex and the columns corresponding to the non-zero entries, then those will actually be they will be linearly independent. You can see why, because if they're not linearly independent, then you can actually perturb the vertex. So extend n with additional columns to get a basis B. Right, so you can always extend it. You can add extra columns to make it a basis, because these are linearly independent and the matrix is is full row rank. So we can extend n to get a basis B of m columns. Now note that AB, so this is of V, must be equal to B. Right? V is exactly the solution of this linear system. I mean, you can technically even look at the square, just looking at A restricted to N, but we'll take a square matrix over here. And what we get is that since the determinant of AB is equal to 1, the determinant is plus minus 1. This is because A is unimodular. Because we assume that A is unimodular. By our previous statement, remember we said that if A is square, has integral entries and is full rank, then Ax equal to B is integral for all B if and only if the determinant is plus minus 1. And so the determinant of AB is plus minus 1. It's a square matrix of full rank. Since the determinant is plus minus 1, by the proposition that we have, V is integral. Okay, so the key is, just to go back and understand this, because it's unimodular, any vertex V can be represented as some solution of some system of linear equations, and that system is given by a bunch of columns that form a basis. It's given by a collection of columns that form a basis. That gives the solution. And because that is the case, we know that we can basically take those columns, construct the linear system, and because it's unimodular, the determinant of that matrix, of that square submatrix, is plus minus 1 because of the unimodular. This is the key point where you use unimodularity. And so by our proposition that we proved, V is integral. So all vertices are integral. Any questions? Any questions? Okay. So now let's prove the other side. So what is the other side? Now we need to say that if Ax equal to B, x greater than 0, x being non-negative is integral for all integral B, we have to prove that A is unimodular. How are we going to show that A is unimodular? We will use this theorem here. So to prove that A is unimodular, we need to prove that essentially all submatrices, so we choose any basis. So let me sort of make this I hope I haven't fudged. Yes, okay. So we have that Ax is equal to B is integral for all integral B. And I want to show that A is unimodular. So choose any basis B of columns. So here's my matrix, and I chose some B, and this gives me my submatrix A sub B. So I want to show, we need to show that the determinant of B has an absolute value of 1. Now we'll go and use our proposition. So our proposition said, by the proposition, it suffices, it's actually equivalent, it suffices to prove that for all integral b, abx so I'm just going to refer to this as abxb, just a solution, because x isn't really n-dimensional, it is m-dimensional, it's restricted to this, is to prove that for all integral abxb is equal to b, the solution of abxb is equal to b. Maybe let me instead say abz is equal to b, where z is m-dimensional. Okay? So by the proposition, it suffices to prove this. If I prove for all integral b that the solution of abz is equal to b, if I prove that the solution is integral, then I'm done. So I'm just going to prove this fact, and the determinant is going to have an absolute value of 1 as a consequence. So the key is to note that this is again essentially a vertex of the polytope. Right? abz equal to b is essentially going to be a vertex if x is greater than or equal to 0. And therefore, because the vertex of the polytope is integral, we will show that that value is integral. So we need to use the fact that the polytope is integral over here. I mean, it's integral for all b. Okay, so we need to show that the solution of abz of b is integral. So consider the polytope. Consider the polytope a x equal to b, x greater than or equal to 0. Now I'm going to state a proposition over here. I'm going to leave the proof as an exercise. And this is really, again, by the consequence of the previous proof that I showed regarding simplex algorithm or during that lecture. So the proposition is that if the solution to abz equal to b is non-negative, then z is a vertex. So you can actually argue that if the solution happens to be non-negative, and that's because it's a basis. So you can argue that if the solution is non-negative, then z is a vertex. So what this means is if z is a vertex of the polytope P. So consider the polytope P of this form. Then z is a vertex where technically z would only have non-zero coordinates along B. So this is z. It has some non-zeros over here, and you just pad zeros everywhere else. This point is going to be a vertex of the polytope. Okay, so we consider this polytope ax is equal to b, x is greater than or equal to 0. So by this proposition, if solution is non-negative, then we're done. Because our aim was to show that the solution is integral. And if it's integral, if it's non-negative, we're done. Because why? Well, then z is a vertex of the integral polytope. Now, if the solution is negative, we will shift the polytope. We will basically shift the polytope by changing b. And again, we know that because by our assumption the polytope is integral for all b, so we'll basically, again, we can just use this theorem. We'll shift the polytope by b so that, and you'll see what I'm going to do. It's once you see the proof, it's fairly straightforward. So pick arbitrary. So I'm going to refer to the solution, just sort of abusing notation. I'll just say the solution is z. Right? That's the solution to a, b, z equal to b. So that's just z. So pick an arbitrary w. Pick an arbitrary w integral such that w plus z is greater than 0. So just pick some arbitrary w. And what we'll do is we'll set b prime equal to ab of w plus b. So I'm just going to move it by ab plus w. Okay. Now note that ab of w plus z is equal to ab of w plus ab of z, which is equal to b prime. And w plus z is greater than or equal to 0. Hence, w plus z padded with extra zeros is a vertex of the polytope x where ax is less than or equal to b prime x greater than 0. Right? Because this was the proposition that we had. The proposition we had that is if you choose any basis and the solution is non-negative, then that solution is a vertex. And what we've argued is that w plus z is non-negative and satisfies this equation with b prime. So we basically shifted from b to b prime. We've just shifted the constants. And so w plus z is a vertex of the polytope. So w plus z is integral. But w is integral. So z is integral. And that ends the proof, because now z is integral. This is exactly what we wanted to show. We wanted to show that the solution of a, b, z is equal to b is integral. So there are multiple chains here, right? We're using the proposition to convert this question about the determinant to just checking that the solution is integral. And this we can now relate to the vertices of the polytope. And the way we relate it to the vertices of the polytope is really, we started with this sort of key characterization here, that the vertices has at most n non-zero coordinates. And moreover, there is this additional proposition that I showed here that saying that if the solution to abz is non-negative, then z is a vertex of P. So one needs to prove this proposition. The proof goes exactly by the theorem that I have over there. Like this, it's the same proof. So when you put all of this together, what you get is a proof of the Venard-Danzig theorem, which says that ax equal to b with the non-negativity constraint is integral if and only if a is unimodular. And so from unimodular, it's actually not too far to get to total unimodularity, and I'll just show you the proof over here. Okay? All right. I will put down the final proof of the Hoffman-Kruskal theorem, then I'll pause and I'll take any questions that you have. So I'm just restating the Hoffman-Kruskal theorem. Ax less than b, so the polytope, this polytope is integral if and only if a is totally unimodular. And in some sense, the proof again is almost like analogous to the analysis of the simplex algorithm, which is, let's say you convert the LP ax less than b, x is greater than 0 into slack form. So we'll convert it into the form that gets it over there. So remember that the conversion was just saying that if ai star x, right, this is some constraint is less than bi, then this, we essentially can convert into ai star x plus zi is equal to bi, and then add the constraint zi is greater than or equal to 0. So that just means that ax less than or equal to b, x greater than 0 can be converted. And now let's write this out in matrix form. So we have the matrix A, and then we have the identity matrix here, because we have this new variable for each constraint, right? And this gives us the slack form. And we have this is equal to b, ai of x and z is equal to b, right? So there are new variables here. There's these new variables, z variables. We have x and z are both non-negative. So this is an equivalent transformation, and this form we can apply the Venard-Danzig theorem. And then we know that AI is essentially unimodular, and then we can show that therefore A is going to be totally unimodular. So we can show that. So let me call this polytope P, and call this polytope P prime. That P is integral if and only if P prime is integral. It's somewhat of a technical calculation. I won't go through it, but it basically follows from the characterizations of integrality in terms of optima. So the optima of one, so we can show this. This is because the optimal values of doing something like min C transpose x, x is in P, is the same as a corresponding optimum in P prime. There's a very simple transformation between the points in P and P prime, and therefore you can show that vertices in one correspond to vertices in the other. So I'm not going to work out that. So we just say P is integral if and only if P prime is integral. And so because P prime is integral, so we're basically saying that the matrix, this LP is integral for all integral B, for all integral B, if and only if the polytope A, sorry, I'll write this, A I x z is equal to B x c greater than 0, only if and only if this is integral for all integral B. I should say over here that this is for all, is integral for all integral B. So this is just an equivalence between the normal form and the slack form, and now we can apply Venard-Danzig here. So the Venard-Danzig theorem says that therefore this matrix AI is unimodular. And then there is another proposition. It's really an exercise that says that AI is unimodular if and only if A is totally unimodular. Now I'll just show you a picture proof. So consider AI. So let's take A over here and take any square submatrix of A. Right? So any square submatrix of A. We want to prove for total unimodularity. So what we need to prove is that the determinant of A prime is in 0, 1, or minus 1. Suppose it's non-zero. Then what we can do is look at this matrix over here. We took AI, so this is A, and this is just the identity matrix. So if the determinant is non-zero, you can take these columns and then take a bunch of other columns here to extend to a basis. So extend to a basis. And this is possible because the determinant of A prime is non-zero. If the determinant was 0, then you couldn't extend, but then anyway, it's 0, you're done. So if the determinant is non-zero, then you extend to a basis. And then the determinant of the basis is plus minus 1. But note that because you basically padded these identity rows, or the columns of the identity matrix, the determinant of that basis is going to be the determinant of A. So extend to a basis B, and you can argue that the determinant of A restricted to that basis is going to be equal to the determinant of A prime. And that's basically the proof. So this is like a picture proof that AI is unimodular if and only if A is totally unimodular. So when you apply this proposition, then you get that A is totally unimodular. And this completes the proof. I'll pause here and I'll take any questions you have before I show the next part. Okay, so now that we have this notion that we have the Hoffman-Kruskal theorem, let us now revisit the polytopes we have in the beginning, and we'll just prove that all of these are totally unimodular. Now, instead of trying to prove that, essentially from scratch by trying to look at all the square submatrices, there is a very convenient characterization. There's a very convenient theorem showing some special case of totally unimodular matrices, and all of these are going to fall into that special case. And this is a very commonly used characterization. And this is a theorem. This is of Poincaré, going back to 1900. And I'm going to leave this as an exercise. It's a fairly straightforward induction. So it's let A be a 0, 1, plus 1, minus 1 valued matrix. Matrix where every column has at most 1 plus 1 and at most 1 minus 1. Then A is totally unimodular. So if every column has at most 1 plus 1 and 1 negative 1, then the matrix is totally unimodular. And this you can argue explicitly by looking at the square submatrices. So when you have a square submatrix where a column has only one non-zero, then it's easy. You just expand the determinant out. And if it turns out that all columns have 1 plus 1 and 1 minus 1, then you just sum up all the columns and they become 0. And so therefore, the determinant is 0. So let me give you a very special, a common example of a matrix that comes up that has exactly this behavior. And this comes up in all our flow and cut settings. So consider the edge, vertex, incidence matrix. Sometimes it's even called the edge incidence matrix. Sometimes it's just referred to as the edge incidence matrix. So what is that matrix? So the rows are indexed by V. The columns are indexed by E. And so consider some digraph G equal to V comma E. So I'll say AVE is plus 1 if E is equal to V comma U. So V is at the head. It's minus 1 if E is equal to U comma V and 0 otherwise. So if you look at any edge, there's exactly one place where there's a plus 1 and one place where there's a minus 1. Right? Because any edge is only two endpoints. So there's 1 plus 1 and 1 minus 1. And so what you get is that this matrix A So A is totally unimodular by Poincare. Now we'll see that in the cut polytope, this is precisely the matrix that we get at the heart of it. So let's go and let us look at the cut. This is the cut sort of matrix. You remember that the objective really doesn't matter because we're just showing that the polytope is integral. So let us look at that. So we have constraints for every edge. We have a constraint. And what we have is a non-negativity constraint on y, but not on z. Okay, so let's just write this out over here. So for the min cut, this is really ST min cut, the constraint is ZV minus ZU minus YUV is less than or equal to 0. We can just put constants for ZS and ZT, so I'm not going to take care of them separately. And then we have some non-negativity constraint for Y's. The Z's, of course, are arbitrary. So let us write out what this matrix is going to be, and we'll basically get something like the transpose of V. So we have two kinds of constraints here. We have the non-negativity constraints that I'm going to put into the matrix because we don't have all variables being non-negative, so I have to treat them separately. So this is YE. So what we have here are all the edges for which you have the non-negativity constraint. This is the non-negative constraint. And again, you have edges over here, and you have the distance constraint. Right? And the variables are of two types. There are the vertex variables, and there are the edge variables. So here are the vertex variables, the edge variables. So here you just have minus of the identity, and here you have minus of the identity. In these non-negative constraints, the vertices don't participate, so that's just a 0. And what you have here is exactly the transpose of this matrix, right? Because every edge is going to participate twice, so you have the transpose of this matrix. So this is the matrix. So it turns out, because A transpose is totally unimodular, you can argue that this matrix is also totally unimodular. So you can show, and because once you know that the determinants of these are plus, minus 1 or 0, if you take in sort of extra columns or a square submatrix with portions of the identity matrix, it's really not going to change anything. So you can show that A transpose minus I is totally unimodular, and then using that you can show that A transpose minus I, 0 minus I is also totally unimodular. So you prove totally, and so this is totally unimodular, and so you can apply the Hoffmann-Kruskal theorem, the first part that says if A is a totally unimodular matrix, B is an integral vector, then AX less than or equal to B is integral. Because we don't have non-negativity constraints, we can't use the main Hoffmann-Kruskal theorem, but we can use the other one. So by this theorem, the min-cut polytope is integral. The min-cut polytope is integral, and this is exactly this is actually an alternate proof. Using this, you can get an alternate proof of Maxwell min-cut. Because once you know that the solution is integral, it's easy to see that integral solutions correspond to cuts, and then then it's fairly straightforward to prove the Maxwell min-cut theorem. So we get the min-cut polytope is integral. It's a very important theorem. Now let's look at min-cost flow. And you'll see that the matrix that you get in min-cost flow is essentially just the transpose of this matrix, because we know that there's this duality relationship between the cuts and the flows. But let me write this out explicitly over here. Okay, so remember that the constraints that we now have are, there is a constraint for every vertex. There is a constraint for every vertex. And then there is a constraint for every edge. And we just have non-negativity. So we can just use the normal Hoffman-Kruskal theorem. We're looking at non-negative. So we have this constraint over here. So I'll break this up as follows. So here I have the capacity constraints. These are the capacity constraints, and this is all the edges. What I have over here is, this is the flow conservation, and these are all the vertices. The variables I have actually correspond to all the edges. So what I have here is an identity matrix. Now this part, I have to be a little bit more careful, because I need to express this. This is an equality constraint. So I'm going to convert it into a non-negativity constraint. I'm going to convert these into inequality constraints by doing the upper bound and the lower bound. So I can just take each of these and say, this is at most BV, and the negation is at most, the negation of BV, and I would get these constraints. And so what I technically get is a picture that looks like this. So I get capacity constraints here. This is identity. I'll get flow conservation. One is like basically saying less than equal to BV. The other one would be less than equal to minus BV. And so I would get these vertices here. I have to sort of duplicate the negation of the constraint. But if you look at any one of these blocks here, this is exactly going to be the edge incidence matrix, because for every edge, it's going to appear in two constraints, once with a +1 and once with a -1. And here it's just going to be flipped. So this matrix is A, this matrix is -A, and then you have the identity, and you can argue this is also going to be totally unimodular, because A is totally unimodular. So this will be totally unimodular. You can argue this by basically looking at, it's again a fairly straightforward thing. When you look at square submatrices that come from two of these, if you actually duplicate two of the rows, then the determinant is non-zero, because one row is just the negation of the other. And otherwise, if you take different rows, then you can just argue that the determinant is going to be 1. Okay, so this proves that the flow polytope is integral. And this is a fundamental fact that I also said is known as the integrality of flow, a deep theorem. So this tool of total unimodularity is beautiful in that it knocks off all of these, it unifies all of these statements. Let's now actually prove the Birkhoff theorem, again by showing that the matrix that you get is totally unimodular. One has to be a little bit more careful there, but it turns out that that you can also prove that. So now I'm just doing the Birkhoff polytope, or rather the bipartite matching. And so what we get here is that, remember, x delta v is equal to 1, x is greater than 0. So now if we look at this, it doesn't look like there's going to be Poincare, and you'll see why. So I take the constraints are for the vertices. What I have here are the edges. Now the edge appears in two constraints, but both with +1, right? So it's going to appear as a +1 over here and also as a +1 here, because I'm just summing up all these I'm summing up for every vertex. I'm simply summing up the variables for each of those edges. And so I just get a +1 everywhere. And so this matrix by itself isn't totally unimodular. Or rather, let me take that back. I have to use the fact that the graph is bipartite, and then I can prove it is totally unimodular. So how am I going to do that? I'm just going to do something very simple here. I'm going to say that technically the vertices can be partitioned into two parts. Remember, the graph is bipartite, so I'll just say you have the left vertices and the right vertices, so VL and VR. And every edge goes between these. So what I'll do is I'll simply negate the VR constraints to minus x delta V is equal to -1. So this is for V in the right side. And for all the left side, I keep them as they are. So essentially, I can negate all of these rows and keep all of those rows positive. So then I can negate these. And then again, this matrix is going to become totally unimodular. This trick does not work if the graph is not bipartite. Because the graph is bipartite and because the edges go from one end to the other, I can get this consistency. Otherwise, this is not true. But then you could, so essentially, because this matrix is totally unimodular, essentially the polytope for bipartite matching, technically for min cost, bipartite matching is also integral. And this gives you an alternate proof, I guess a more complicated one, but a unified proof of Birkhoff's theorem. So this sort of shows these three important examples, important polytopes, and why all of the matrices that we get from there are integral, and that stems from the fact that the matrix is totally unimodular. There is a generalization of this notion called network matrices, which I won't get into. Just at the end, just to show you the relevance of this and why I think it's important to know this, even if you don't work, let's say, in the theory of algorithms, is a very interesting paper that I came across recently. This is by Davidson and Ravi, and this is in AAAI 2020, so very recent paper, and show that fair clustering LPs are totally unimodular. It's a very specific kind of fair clustering, but I believe some of you have probably seen fair clustering at some point. And so you can think of it as, I'll just give you an example here. At the end of the lecture, I'll take any questions. So you have n items assigned to k clusters. There is a protected group, or a subset of items, subset S of items. And we want to maintain that the number of S items in ith cluster should have some upper and lower bounds. So you want to find a clustering that satisfies this property. The number of S items, so you want to cluster everything, n items to k clusters, but for each cluster you have this constraint with respect to the protected group. And this is usually, the lower and upper bound would be something like this is the base population rate or something like that, and you have some slack in these constraints. And so what you can do is you can actually write an LP which is not, where if you look at the LP doesn't have integer constraints. So it doesn't say that you have to assign every item to every cluster, every item to a unique cluster. It allows what's called a fractional assignment. But Davidson and Ravi proved that the matrix that comes out of it is actually totally unimodular, and hence all the vertices are integral. And because of that, this problem can be solved in polynomial time using an LP. And it's a very, it's a very nice use of total unimodularity. And I'll just write down quickly what the LP is, and you can ask me questions about it. So you have a variable, a non-negative variable xij, which is just, this is just like the assignment of jth item to the ith cluster. So think of this as supposed to be in 0 or 1. This is like an indicator, right? So that would give an integer program, but we are just going to simply only have a non-negativity constraint. And so what we have is that, for all clusters I, summation j and s, xij is at most the upper bound, j and s, xij, this is at least the lower bound, and we just have for all items j, the summation over I of xi is equal to 1. This means that I has to be assigned to some cluster. And this is actually totally unimodular. So I will end now, and I just wanted to show this example to show you that the total unimodularity is something that repeatedly comes up in optimization. So I'll be happy to take any questions you have about any of these things. I'll stop the recording now.